Hello everyone, and welcome to this introductory session on RedisGraph. My name is Daniel D'Agostino. I am a software team lead at Cleverbit Software, a company based in Malta. I've been working in the software industry for more than 10 years, and my main focus is .NET development. I've also been writing on the web since 2002, and I've run a number of websites and blogs, and nowadays I also write articles professionally. When we talk about graphs, typically we mean a network of entities that are interconnected in potentially complex and intricate ways. You could think of social networks, family trees, organization charts, and a lot of other real-life examples. The graph we are seeing in this example is oversimplified. We just have nodes, the circles, and edges or relationships, the arrows. In practice, we'll be talking more about property graphs, where both the nodes and the edges can carry additional information. There are a lot of graph databases to choose from nowadays, but we're going to focus on RedisGraph, which is a relatively new player in this area. RedisGraph is built as a module for Redis and is extremely fast. It's also very easy to use, and we can interact with RedisGraph using the Cypher language, which is also used in some other graph databases. RedisGraph uses sparse matrices to internally represent the graph data. It also leverages the highly optimized GraphBLAS library, which gives a combination of extremely high performance and very compact storage. It's also interesting to understand how RedisGraph handles requests. Now we all know that Redis is single-threaded, and that's how incoming requests are handled even for RedisGraph. However, once a RedisGraph query reaches RedisGraph, it is passed on to a thread pool, because nowadays Redis modules can actually manage multiple threads. Now, if you look at how other graph databases service queries, typically what they do is they spread out the query across all cores of the machine, trying to exploit parallelism. RedisGraph doesn't really do this, and it's focused more on high throughput scenarios. So, one query at any given time will typically run on only one thread. This might sound counterintuitive, however benchmarks show that this scales really well. If you want to try out RedisGraph, I suggest starting by looking at the RedisGraph homepage. If you scroll down a little, you can see the command you can use to run it under Docker, which is by far the easiest way. So you can come here, copy this, add sudo before it, and run it. If you'd like to try out the latest features, just put :edge at the end. So once you have RedisGraph running by means of Docker, what you'll see is an instance of Redis running that already has the graph module loaded. The same graph module actually manages a thread pool like we said before, so you can see this in the output. Once you're a little bit more comfortable using RedisGraph, you might want to install it in a more serious environment. If you're running your own Redis cluster, you can actually load RedisGraph as a module into Redis, and you'll find instructions to do this further down on the same page. A third option for bigger scenarios is to use Redis Enterprise Cloud, which is a managed Redis service. In terms of client tools, we can interact with RedisGraph using the good old Redis CLI tool. We can also use the newer Redis Insight tool, which provides additional benefits such as visualization. If you want to interact with RedisGraph from a programming language, check out the various client libraries available for Python, Java, Ruby, and other languages. So let's take a look at a very simple example. Hans loves cheese. Simple as that. 2 nodes and a relationship. In order to create this in RedisGraph, we're going to use the Cypher language. And this seems like a bit of a combination between ASCII art and SQL. So this is a typical command we would run in Redis CLI, and it looks a bit weird because it's actually a Cypher query within a Redis command. So the first part, graph.query, is a Redis command just like get or set. My first graph here is the key, so the whole graph would be stored in this key, and the parameter in quotes is the Cypher query itself. Let's look at it separately to try and understand it. So this whole thing makes up a Cypher query. Create is the command, so that's kind of what we're trying to do. There are a few others like match, for example, which we'll see very soon. Then we have some parts in round brackets, like this one and this one. Those are the nodes. And the arrow here is the relationship. So you can see visually the query looks very much like what we had in the diagram here. Each of these 3 parts can have additional things inside it. So for example, here we have Hans, which is like a label or a variable name. We have a type, which is person, and then we have additional properties in what looks like a JSON structure. We have something very similar here for cheese. In the case of the relationship, all we have is the type. So note that not everything you have inside a node, as we can see here, is required. A lot of these things are optional. Okay, so we can actually grab this whole thing, fire up good old Redis CLI, and run that as a Redis command. And we can see that something was created for us. So at this point, we can start running queries. Now I've already prepared some that we can use here. So the easiest thing to do is to simply list all the nodes, and for that we use a match query. Okay, now the match query will look for a pattern, which in this case is just a node, and we're giving it an arbitrary name, which is X, and we're saying once you find something that matches this pattern, return that X. And that will give us all the node data, which you can see is a bit verbose. We have a lot of metadata here. So perhaps we just want to get the name. You can do that using a dot notation, very handy. Okay, now some of the more interesting queries come when this pattern includes relationships. So I have one prepared here that we can try. So we're saying, look for a pattern where you have a node X and another node Y and a loves relationship in between them. Now the names X and Y are completely arbitrary. And once it matches this pattern, it's going to return the name of each of those 2 nodes. And we can see we got similar output to what we got before. Now, something interesting also is that we can actually visualize this. So if I take the Cypher query only, not the rest of the Redis command, I can go into Redis Insight. Okay, it's a tool by Redis Labs, and it allows us to do a lot of things with Redis instance. So I'm here right now in the RedisGraph section, and I can go here and paste my query and press play or execute. And this actually gives me a visual representation of the graph. I can zoom into it a little bit, I can also view it in a table view if I want. Okay, so very handy. Doesn't look very useful for this small example, but it's very handy for bigger ones especially. Okay, now if we go back to Redis CLI and we use the Redis type command, so it gives us the type of a key as it's suggesting here. We can see that the type of our graph key is a new type called graph data. So that's something that RedisGraph brings into the picture. Okay. Now, if we want to delete a graph, we can do that using either the familiar del command or graph.delete. Both of them do the job, okay? It's just the output that varies a little bit. Right, so how can we load data into RedisGraph? So one option we have just seen, it is to write Cypher queries using the create command. Doing this one by one, it can get a little bit tedious for bigger examples. So another option is to still use create commands, but pass them to Redis CLI using pipe mode, which we'll see very, very soon, instead of simply pasting them one by one. For scenarios with much bigger data, there exists a bulk API. It's graph.bulk, and this is as yet pretty much undocumented, but if you need it, just know that it exists. And there also exists a bulk data loader utility. It's on GitHub. So for the rest of this session, we're going to look at this particular example. It's a big enough example that we can run some interesting queries, but it's small enough that we can visualize it and compare the results we see in Redis CLI with what's in this image. So, as you know, right now, unfortunately, we're living in COVID-19 times. It's a hard time for a lot of people, and the authorities are having to take a lot of hard decisions. And hopefully, when they do that, they take these decisions based on data. Okay, so over here, I have a completely fictitious example of how a disease may have spread from one patient, who I'm calling patient 1, to a number of other people. So we also have a few properties. So for each patient is a node here, okay? For each patient we have the day they got infected. Some of them have a day when they got cured. Others have a day when they died. Not all of them have these last two properties, because the idea is that things are kind of still ongoing here and not everyone has had an outcome. Okay, so just by looking at this graph, we can already see a number of things. First of all, that even though patient 1 infected only 3 people, the net effect of the spread was that a lot of other people got infected from that. A total of 28 here, if you count patient 1 as well. So we can see that there is a certain breadth, okay, that the disease spread from one person to another relatively quickly at the beginning, and then it started spreading a bit more slowly. So eventually, just one person spread it to just one person, or maybe it stopped there. And also you'll see that there is a certain depth. So like through patient 4, eventually we stopped over here in this area, but through patient 2 it kept going all the way here. So it took a very long time to eradicate. Okay, so let's see how we can actually load some data for this. So I have prepared here a file full of basically create commands. We're going to be using this disease graph here. So you can see the first part of the commands is always the same. And what we're doing here is in the first section, so up to here, we are creating the patients, okay, by themselves initially. We're giving them a name, we're giving them a day when they got infected, and some of them have additional properties. So the day they got cured or the day they died. The other queries over here are a little bit different. Since we already have the patients and we're not going to insert them again, what we do is we match them. So we look for two types of patients. Okay, so we have in this case patient 1, for example, and patient 2, because patient 1 infected patient 2. So we look for patient 1 based on the name, and we name that infector. We do the same with patient 2, but we call it infectee. Okay, so it's an arbitrary name here. And with the results of those two matches, then we go ahead and create the relationship infector, infected, infectee, as you can see here. Okay, so I've got a text file with all these, and we can populate this graph on RedisGraph using Redis CLI pipe mode. And this looks like this. It's actually very simple. So you cat the text file I just showed you, and you pipe it into Redis CLI with the --pipe argument. So this file is called disease-load-data.sh, which is this here. And I'm going to go ahead and run that. So you can see that we got 55 replies. And since this is in place, we can now start running queries in Redis CLI. So we can start off with the most basic. Okay, basically return all the nodes, and you can see we have a lot here in the response. So again, like we did before, let's maybe just return the names. Okay, that's a little bit easier to visualize. So then we can start adding more interesting things like this where clause, which, you know, makes it look a little bit more like SQL maybe. Okay, so here we searched for all the patients who got infected before day 3, and it gave us 3 results. Okay, so if we combine the where clause with this exists function, we can get some more interesting information, like give me back those patients who died. Now, since not all of the patients have this died day property set, the exists will give us back only those nodes that have a value for it, which in this case is patients 2 and 9. Now we can do the same thing for the cured patients, and we can also negate those two and get everything else. You can see where not exists, so give me the people who did not die and also the people who were not cured. Okay, and the results here, you'll notice, do not overlap with those from the last two queries, which is what we expect. Okay, now an interesting thing to consider here is the spread. You know, how fast is it spreading? What is the replication factor? And in a graph, each node has an in degree and an out degree. So the in degree is the number of arrows coming in. You'll notice for this particular example it's always 1. So that's not very interesting for us. But we also have the out degree, and the out degree is the number of arrows leaving the node. In this case it's 3 for patient 1, for example. So the out degree in the case of the spread of a disease gives us a measure of, you know, how fast it is spreading, and in the beginning it's quite fast. So I have like 3 people and then 2, And towards the end, it kind of fizzles out. So you have 1, you have like 0. So that's pretty interesting. And let's see how we can get some insights out of this as well. So we can simply go over the nodes and use this Outdegree function. And that will give us a number for each node. Okay. Now we can also start using aggregate functions. Again, some of these might be familiar if you know SQL. So we use avg for average, and this gives us the average Outdegree for all the nodes, which is 0.96 something. Okay, now if we take this average, okay, for a restricted number of nodes, like let's say for the nodes that, you know, the patients were infected before day 5, let's say before some lockdown measures were being taken, we get an Outdegree of 1.7, which is quite high. But on the other hand, if we check the Outdegree for the rest, so those that got infected from day 5 onwards, we see that we get an Outdegree of 0.5 recurring on average. So that shows that whatever isolation and containment measures were taken by the authorities seem to be working in this particular example. Okay, some more statistics we can get are the number of people infected each day. So in this example, we're looking at, so we're going through the nodes and we're getting the day they were infected together with how many were infected on that given day. Unlike in SQL, we don't need to have a group by clause. So here we get kind of tuples, okay, so like for the first day here we have 1 that got infected, for the second day we have 2, and so on. This is a little bit hard to visualize here, so we can tweak the query a little bit. You'll notice we're also using string concatenation here, which you can use as well. And, you know, the output is a little bit more manageable. So potentially from this data you can build one of the graphs that we've been seeing a lot in the news. Okay, again, some of the more interesting queries can be about relationships, okay, so matching patterns. So here we can see who was directly infected by patient 5. And patient 5 we can see directly infected only 2 people, 12 and 13. So if we take that query and okay, run it here, we get patients 12 and 13. Okay, now we can do a similar query. Okay, so we take this query here and you'll see it's almost the same, but it's got this asterisk 1 dot dot, and that means that instead of just matching this pattern as it is, we can have one or more of this infected relationship. So what that effectively is doing is, here instead of looking at the patients directly infected by patient 8, we're looking for anyone infected via patient 8. And we're doing a count, so we're getting 5 people. If we look at patient 8 here, we see we've got 5 people directly or indirectly infected from there. Okay. So some of the more advanced queries we can do are about paths. So if we look back at the graph, we see the nodes in red, for example. So we can say, okay, how did patient 1, maybe through other people, ultimately end up infecting patient 28? And we do that by doing queries very similar to what we just did, but we assign the pattern to this path variable. And in the end, we can use this node function to get a list of the nodes along that path. Okay, so what we see here is a list of nodes with internal IDs. So this doesn't tell us much about what's in the node so far. We could potentially take those internal IDs and look them up, but we could also elaborate the query a little bit, maybe complicate it slightly, and use the unwind keyword to extract the nodes from that list. And like that, we can pull out the name and get a more readable list. Okay, so we've mostly seen querying capabilities of RedisGraph. However, it's capable of full CRUD, so you can also do updates. Like patient 7 was cured on day 16. So we can do an update there. And you can also delete nodes. So maybe patient 26 was erroneously diagnosed and you want to remove them from the graph. And you see that delete removes not only the node, but also any relationships touching that node. Okay, just a final point about indexing. So let's just take an example query. Okay, so we're looking for people infected directly by patient 10, and we can actually change graph.query to graph.explain, and that will give us a query plan. So we can see here that we have all node scan, and that's kind of bad news because it's like a full table scan in SQL. So what we can do then is we can create an index, and a lot of our queries involve the name property. So we can look for nodes of type patient, which is everything in our case, and put the index on the name property. So if we run the explain query again, what do you think we're going to see? Nothing has changed. We're still using an all node scan, which is not good. So the problem here is that if you look at all the queries we've used so far, we've been a little bit lazy, and we simply specified a variable name when matching nodes, and we didn't specify the type. Now in our case, it's okay because all the nodes happen to be patient nodes, but in order to fix this and to make use of the index, one thing we can do is to specify the type. So we go over the nodes in the query and we specify that the nodes are of type patient. And like that, we're using an index scan, which is great. For this example, it might not make a huge difference, but if you have a lot of nodes, it's definitely going to have an impact. Okay, so that's all I had. I have a number of links here in case you want to learn a little bit more about RedisGraph, and just to go through them quickly. So you can read more about how RedisGraph works internally. A lot of details here if you're interested in that. You can see some of the original benchmarks of RedisGraph 1.0. Having said that, RedisGraph 2.0 came out quite recently, so it's even faster than 1.0. And if you check out the RedisGraph homepage, which we've seen before, and you go to the commands section, you can see a lot of documentation about the various queries that you can do. I've also included links to a couple of articles I wrote back in November 2019, where you can see a couple of hopefully interesting examples: company shareholding and a family tree. Okay, so thank you very much, and I hope you enjoyed the rest of RedisConf.